Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
For this afternoon. There's a theme to this last set of talks, as I hope you're seeing. Over the course of the program, I've tried to bring talks together from the collection of funded work that in each session more closely resemble each other than some of the other talks. In this case, for the afternoon, I would like to share 3 talks that focus on various aspects of performance optimization for managed executables in dealing with aspects of linking and instrumentation and so forth. The first of these 3 talks will be given by Alex Buckley. Alex works under Susan Eisenbach at the Imperial College London in the UK. Susan is a teaching fellow at Imperial College. Her research interests include versioning, dynamic linking, specification of programming languages. Alex is a second-year PhD student supervised by Susan and Sophia Drzopoulou. Very good. Okay. He works on flexible dynamic linking, which is the focus of this talk, a scheme to help bytecode use the best classes available at runtime, so increasing reusability and decreasing development costs. Alex.
Am I on?
You're on.
My name is Alex Buckley. This is joint work with one of my supervisors, Susan Eisenbach, and one of our project students, Anders Altonen. So I'll introduce dynamic linking as it occurs in the CLI. I'll discuss why we believe it to be a little inflexible and how we can make it more flexible and how we can retain safety at the same time and how we can do that by putting developers and programmers at the heart of the linking process. I'll discuss some design issues with bytecode engineering on the CLI and then talk about where we are and where we're going next. So dynamic linking at the highest level takes an instruction with a member descriptor, a reference in the CLI to an assembly, a class, and either a field or a method signature as referenced by a load field, store field, callvert, all those kind of instructions that was generated at compile time, and at runtime turns that into a direct reference to an object or an offset that could be used to look up fields and methods in objects on the heap. And it does that, of course, by loading assemblies and classes as described in the member descriptor, loading those resources from disk, inspecting them, finding the offsets, and so being able to directly access a member of an object on the heap. So it's taken as given in modern execution environments like the JVM and the CLI that dynamic linking will be present. There are well-known benefits. It saves space by allowing code to be reused between different programs. There's no need to build a monolithic executable when you can download assemblies and classes at runtime onto the user's machine. And particularly in the CLI, it enables binding policies such as I'm an assembly and I'd like to refer to, and I have a reference to version 1.0 of some other assembly, and the user or the systems administrator or someone can specify actually there were some serious bugs in 1.0, use 2.2.0 instead. There are servicing policies that differ from one version of the CLR to the next, but that generally say things like, if I have 1.1 something and there's a 1.2, a minor version upgraded, available on the system, use that silently and automatically. There are policies that it enables, such as unification, which is to say if I'm running on, say, the CLR 2.0 and I'm an old application and I refer to version 1 of things like MS-Corlib, then silently the linker fusion in the CLR will give me version 2 of MS-Corlib to be in sync with the runtime, the CLR runtime itself. And of course, you can implement policies to probe the local and remote file systems in some order, check the GAC first, go and look at a URL. You can start to design those policies because you're putting the code in at runtime. And of course, I mentioned member descriptors before, because you're linking, because you are resolving very rich types, an assembly name, a class name, a field or method signature. You have that type information available on the user's machine, so you can do verification, subtype checking, data flow analysis at the very last possible moment before the application runs. So a quick overview of how assemblies, what metadata assemblies contain that's useful for dynamic linking. If I have some some IL that is a call instruction, for example, and has a very fully qualified method signature referring to the muscallib core assembly, where an awful lot of the CLI's APIs live. I have a class name, system console, and then I have a method signature, write line, that happens to take a string and is void, so ignore the return type. So to execute that IL, there will come a point in JIT compilation and linking where the current assembly's metadata is checked for the mscallib import to get a strong name for the mscallib assembly. That strong name will be passed to the linker, which is Fusion in the CLR. That will implement policies to go and find the muscallib assembly of a particular version, etc. Will return it, and then one of the exported classes from that assembly is hopefully system.console, or console in the system namespace, and then we can start to inspect that, find the offset for the write line method, and eventually be able to make a reference to that particular function. The issue is, though, that for one thing, most languages do not let you specify the assembly. When or at least you declare what assemblies you're going to use, but when you come to write the code, you refer to class and member names only. So if I write console.writeLine in my source code, the compiler is the guy that makes the decision that says this is going to come from the mscallib assembly. You declare that mscallib is a fine possibility for the source of that class, but actually you don't have very much control over that. So you get embedded into the assembly that you generate references to these other assemblies. mscallib will be in every single one, almost certainly, and others. And that actually is a very aggressive decision by the compiler. It doesn't have to be that way. You could imagine that if you have other assemblies available at runtime, the mono version of mscallib, for example, which also has fine implementations of 99.5% of the mscallib APIs. That might be a fine assembly to use as well on the user's machine. But like I say, the compiler makes that decision and says, no, you're going to get this exact version of this exact name of this exact assembly. So if you have platform or vendor-specific assemblies, for example, you compile against generic ODBC libraries, classes and some generic ODBC assembly, but the user has installed SQL Server, and that comes with some optimized version of the assembly, some optimized version of the access routines that implement the same interface, but maybe the assembly has a slightly different name, or a version that wouldn't otherwise be found by the standard binding policies. Maybe you compiled your program against the CLR 11's standard FTP classes in mscallib, but those, I think it's Power Solutions, those guys have come up with secure FTP classes in a separate assembly that implements the standard Unix-style FTP libraries, and you would like to be able to use those as well. So one example is we have a model checker at Imperial that has a plugin architecture, so you can plug in various software analysis modules, and NASA wrote some module that plugs into it. We cannot redistribute their algorithm. So the question is, when you're building a plugin architecture or a product based on a plugin architecture like this, how do you avoid static references to someone else's plugin? The answer is you do lots of software engineering. You use proxies, factories, you do introspection, you do all the structural reflection we heard about before, and you almost certainly have typecasts. Maybe from the, if you're loading classes from disk, you'll want to cast them to whatever the interface is that everybody has agreed to support because they're a plugin. And you're using reflection, and these are potentially error-prone. I accept that it's systems programmers who are probably writing this plugin management code. But nevertheless, reflection, casting, and the use of arbitrary patterns like the factory pattern to hide implementations and to hide class names from in your code are ad hoc. There are many of them. It's something you have to design, and then you decide in version 2 you want to redesign your plugin architecture. So in other words, trying to reduce the dependency that your code has on the exact implementations available at runtime is ad hoc at the moment. So to summarize, how can I bind to what's best in the runtime environment when at compile time the compiler forces its choices on me? Or another way of saying that is, instead of the library, instead of the implementation, instead of the class, how about I link a class, modulo type safety, and some other issues, so that, for example, I could say, I could refer to a class name in my source code because I've got to be able to compile and test and deploy on the programmer's machine. I compile against the dblib class, that's okay, but if at runtime there's a SQL Server library class or assembly, whatever the resource is, maybe that's a fine thing to use as well. I don't want the JVM has the same issue. You cannot avoid naming that class in bytecode in the new obj or the whatever the equivalent Java instruction is. Similarly, it ought to be possible, if I'm saying that you make your decisions about what classes to bind to at runtime, it ought to be possible to be able to write this line of source code and compile in a totally empty compilation environment. There's been some theoretical work on this. And then at runtime, again, you find whatever the classes are that's available, you check that they are structurally satisfactory for your application, and you select one on the basis of some as yet undescribed mechanism. So you ought to be able to do both of these things more easily with the scheme I'm outlining. So the initial idea is take this bytecode and abstract it. Use type variables rather than concrete assembly names, both there, so that at runtime, link time I should say, you can substitute that X for mscallib, because that's the guy that provides system console writeln. And similarly, you could do the same thing for classes. Abstract the class name into a type variable, and then at link time, choose a particular class from the specified assembly that has the specified signature. That would enable late binding between the program and the environment, which is what dynamic dispatch is, so it's analogous to that. It would let you avoid naming a specific assembly. So I also accept this is slightly going against the principle of strong naming and being sure exactly which version of a DLL you're going to get. But conceptually, you could imagine times when you would want to avoid naming a specific assembly. You might have multiple versions, all with the same name and slightly different development numbers. And you'd like to develop against one exact version of those assemblies, and then maybe offsite, and then deploy using things with the same signatures, the same classes, maybe slightly different names. You can't do that with Fusion today. You can specify in app config that you want to reversion an assembly, but you can't specify you want to rename it to use a totally different name. And similarly, you might want to use a particular assembly and a particular interface within that assembly, but you will want to avoid naming a specific class. So you might want to use the list interface, but you don't want to name in your code the exact list implementation, array list, hash list, whatever it is, because the user may have different versions. This may be something you want to decide when you look at what the data is at runtime. So you might imagine you've got this flexible bytecode where you're going to substitute type variables to real assemblies and classes at runtime. Obviously, you should do this in a type-safe way. So you could imagine going through the IL, gathering constraints that would say things like, this assembly X seems to have some class system console or an interface list in it. That interface or class provides or should provide certain methods with certain signatures, and you can imagine some subtyping constraints as well. So you can imagine collecting all those things from bytecode at compile time, putting them somewhere in the metadata of an assembly, and then using them at link time to find suitable assemblies from the GAC. This is nice in theory, but it's not impractical. It's messy in real life. For one thing, you would need to collect subtype constraints at compile time to ensure, obviously, all the typing will work out at runtime. And collecting subtype constraints almost always requires data flow analysis, and that's what the verifier in both the CLI and the JVM do. A large part of their activity is to do data flow analysis in order to infer subtypes, in order to check assignments and method calls for type correctness. And also, if you can imagine that if you have an awful lot of code that you're compiling, some of it's unreachable in some circumstances, and you're doing a static analysis to gather these constraints, you're going to over-constrain your choices at runtime. But the main thing is, if you gather all these constraints that talk about signatures, signatures aren't specifications. The fact that I have an assembly over here that just happens to have the right classes with the right method names is obviously no guarantee of behavior, and it is unrealistic to expect that arbitrary assemblies are going to be picked just because they have the right signatures that the programmer has never heard of and has no chance of debugging should something go wrong. So we say this: the programmer, in all reasonable situations, has to know something about what's going to happen at runtime. They have to know, maybe they've tested them offline, maybe they've bought them in and they've got some guarantees, but the programmer has to know valid assemblies and classes that he can link against. So he can specify these through custom attributes, which we like very much as a descriptive mechanism. He can specify that in the code he has developed against assembly 1. That's what's named in the code, that's what's declared in the C# imports. But actually, if at runtime you have an assembly 2, use that potentially instead of assembly 1, or assembly 3. We don't mind. These are options that the programmer is aware of. Simply for classes, if you're using class 1 in the source code, allow the possibility of class 2 or class 3 at runtime. And you would imagine that you would build up families of these attributes in sort of sensible ways, so that assembly 1 actually contains class 1 and assembly 2 probably contains assembly 2, etc. In other words, all types, both assembly names and class names in bytecode, become type variables. They are all substitutable to different assemblies and classes at runtime. Somewhat distressingly, you still need to gather member constraints that say assembly 1 is going to have class 1 and it's going to have the signature of a method or field. You still need to do that, because otherwise you will be loading assemblies that the programmer has said are okay, 2 and 3, or either assembly 2 or assembly 3. But it will be nice to ensure that the verifier isn't going to throw resolution errors when it comes to start looking at the signatures of things that the programmer actually calls. So you can add these custom attributes to specify the programmer's intentions, but of course you can add custom attributes in many places, and that's a nice thing here, because there may be many areas of your code that do not require this flexible linking process to be undergone for the references you make in that code. And so you can minimize the impact of this modified linking process by only surrounding the right, maybe it's the whole assembly, or maybe it's just a module, or maybe it's just a particular class, or maybe it's just a particular method, with an attribute that says, actually, think about linking in this other way, think about loading in this other way. And so you could do a useful thing like say, actually, in this assembly I want to admit the possibility that the list class can be substituted by fast list or doubly linked list or whatever it is. You can specify that at the assembly level, and then you can imagine having some methods that add their own possibilities for the list implementation that depend on what the body of the method itself is doing. Maybe it needs it doubly linked in some particular way, and by declaring link class list up there and then link class list down here, at runtime we will look for the most local attributes and use those to determine the substitutions. So then you get into this issue, which is to say you are naming some potential substitutions. Assembly A1 can be implemented by ABC on Windows 32. It can be implemented by some other assembly on the Win64 platform. You could imagine, I should say, I'm only using flat names here. You could imagine that these things could be strong names. There would be no reason not to do that. We just didn't implement it. Everything is just a basic display name, but that's not inherently a limitation of this. And the point is, if you start doing linking and you decide that A1 should in fact be substituted by the ABC assembly, you probably want to stay within this sort of conceptual Win32 family of assemblies. And similarly, if you choose that way, you probably want to stay within the Win64 family of assemblies. So we have some policies that try to cover all the options that a programmer would want to do, which is to say, the minute I choose a substitution within this Win32 sort of conceptual interface, I demand that you therefore stay within it for all later substitutions at whatever the level of this attribute is. Or you can imagine saying, I want to try other substitutions from Win32 first, but if those assemblies are physically not found, feel free to go and try other interfaces. You might imagine wanting to, and these are all implemented, you can imagine wanting to, the minute you select a substitution from this Win32 interface, you would want to be very sure that all substitutions from Win32 are possible. So go and eagerly load every link assembly in this module that mentions Win32. go and load all of those assemblies that could possibly be substituted, just in case. That's a policy. Maybe that's useful to some programmers. And then, of course, there's the default one, which is I actually don't care about this interface thing at all. Load whatever works. So I'll quickly say the scheme we take overall to make this happen. If you write your, say, C# program and you compile it to XE or DLL, first principle, we insist, like I said before, you must be able to compile this in some environments. This is not truly independent compilation where you truly don't know until it's on the user's machine. So you must be able to compile and run on the programmer's machine. Having got that XE, we disassemble it, and we work, as most of us do, on the bytecode, because there are many compilers, and I'll refer later to a particular limitation or a particular policy the C# compiler has that makes life difficult for us. So we end up with some bytecode that has, of course, the attributes that the programmer specified. We will go and infer these member constraints and add those into the IL, and then we'll reassemble into an executable. And of course, if you then take that executable, it has all these custom instance properties. And if you run that on the standard SSCLI or CLR, they don't mean anything to anyone, and so they're totally backwards compatible. If you run them on our CLI implementation, they will obviously be taken notice of. So when I say taken notice of, what I mean is we will modify the JIT compiler to substitute, to implement those custom attributes, or rather to act on them, at a time that is, what's the word I should use? A time that fits with the CLI specifications policies on how to do linking. So if you read the ECMA CLI spec, there's a deep in chapters 6 and 9, there's a bit that says linking is flexible. Verification may or may not happen. So verification is demanded in the JVM specs. It is not demanded in the CLI spec. And its timing in the ECMA spec, this ECMA CLI spec, is if it happens, it can happen any time. Similarly, that resolution process that takes a member descriptor and goes and loads the relevant assembly in class and works out the offset, you can do that at install time if you like. You could essentially install a .NET application and essentially at install time build a static executable out of it where everything is fully linked. That's perfectly in line with the CLI spec, and it doesn't happen in any implementation, but you could do it. Actually, the CLR and the SSCLI are lazy. At JIT compilation, verification happens, and in order for verification to happen, you have to have loaded the assembly in class, so you have to have resolved it. And so we modify that resolution process to handle these extra attributes that are going to say, actually, you see this assembly A in the reference, in the metadata, try loading this other assembly instead. So it's sort of the wrong way up, but there comes a point where the JIT compiler is compiling a method, a bytecode method, and there comes a point where it needs to, like I say, resolve these member descriptors. And so there's a whole family of methods in CE info: find class, find field, find method, get signature, get arguments, all of which take the IL in the method being compiled and resolve them. That is to say, see if this signature has already been loaded from or tokenized from a class that's already been loaded from an assembly that's already been loaded. There's a standard resolution process concerned with caching and then maybe calling down to the assembly and class loading process that eventually hits the file system. There's a standard process for that. We intercept that if there are custom attributes about link assembly and link class around, and we start our own process of deciding what should actually be loaded. So we leave all this stuff alone. We use the standard assembly and class loading processes. We just modify what they're after. So when a particular IL instruction comes to be JIT compiled, we create what we call a link context that comprises three things. It's the name, AC, and then the method signature that needs to be resolved. It's the most appropriate local link assembly and link class attributes that the programmer specified, modulo which interface they're coming from, like I mentioned before, and also the member constraints that we previously inferred and put into the bytecode. And so when you start to JIT compile a method, we gather the last two of those things. We put those in a master link context. That's a one-time only thing, so that every time we then come across one of these instructions with a member descriptor here, we've already got the last two things complete, and we now know the third thing we need to know, which is the actual name of the reference to resolve. And there is an interesting point, which is that you need to build one of these link contexts, not just for the local method that's surrounding this instruction, but you also need to build one for the target. And the reason for that is, suppose you're resolving some IL that looks like that. You've got this master link context that says, I want to substitute A for B, whatever it is, and you know how to, in other words, you know how to choose for A and C, and you can go and load that substitute assembly in class. But in that substitute assembly in class, there is the definition of the method M. And it, in that definition, in that remote assembly, may also have attributes that say, actually, consider as a possibility for D some other class, consider as a possibility for E some other class. And so that method, when it expects to run, expects to have those remote attributes taken into account. So as well as JIT compiling this line and looking at the local custom attributes from the call site, we also have to look at the callee site as well, and create a link context for that, and they get nested, and it all works out in the end. 5 minutes. So I'll just identify two issues that are kind of bytecode level engineering, what happens when you actually try to do this. And it's kind of a gotcha. We found a couple of these. So you can apply custom attributes to fields and properties and all sorts of stuff. And so here's a typical use of a field, and you instantiate it immediately. And of course, what that compiles to is the constructor for this class A, where the field is. The constructor is the guy who actually does the object instantiation and assignment to A's F field. So if you've written some custom attributes for that field, they're kind of in the wrong place, because you can see it's actually execution of the constructor. Here it is down here. It's execution of the constructor that needs to choose potentially B going to C and whatever the other attributes are. So we could try and recognize this kind of bytecode pattern, where you do in a constructor, if you see a new followed by a store field, that means you're assigning to an instance variable, a local field, and apply resolution there. Because otherwise, that B is indistinguishable to any other B, and you don't know that it's the constructor's one. You don't know that it's this assignment that's happening. So what we would actually do is rely on an IDE to say, if you've written this kind of code, you've got a field assignment going on that you want to be flexibly linked, actually you're going to have to move this kind of these attributes down to the constructor as if they've been there all along. Only then will they take effect. One last little thing that's not so little, actually. So I mentioned before I don't want to rely on compilers, and here is a reason why. The C# compiler resolves fields statically. So if I have this code here, class A declares a field F, and a subclass doesn't shadow that field, then any time I say this kind of code here, new b.f, the C# compiler will compile that to this line here, which is to say, load the field F from class A. The C# compiler sees that the field F isn't in B, it's in A, and it embeds that information, that F is in A, into the bytecode. Problem being, if you naively say, well, look, this is the source code I've written, I want B to potentially be a C, but then I actually execute this line of code that has an A in it, there is no way to know that actually I want this attribute to apply, because it's mentioning a B and we're actually executing an A. Now, this behavior, and of course, if the C# compiler, when it saw this field access, put even the static type of the enclosing expression B into the bytecode, so it said B : F, we would be okay. Java had this issue as well. In Java 1.3, it did what the C# compiler today does, and they changed it in JDK 1.4 to be more dynamic and to mention the actual the actual class where f is visible, which is in B. So it's more akin to a method doing dynamic dispatch. So that's an issue we kind of just hit with this version of the C# compiler. There may be other source languages that do not have this particular kind of static field resolution that trips us up. So I will summarize by saying the CLI we like very much as a place to do this more flexible dynamic linking process. For one thing, there are many implementations, API implementations and runtimes that, in other words, provide many implementations of class libraries, so there is the potential for multiple implementations of lists and FTP classes and database access, etc. You tend not to get that in the Java world. We like using the metadata to guide this resolution. As long as you can find, I'm sure you've all had this, as long as you can find the right level in the JIT compiler, then you can act on these facts. The bytecode that we essentially execute after performing these substitutions is still verified. If we were to choose to verify it, it would still be verifiable. It would still be type safe because it's it has all of the type correct signatures that the original code had. And like I say, tiny amounts of code under 100 lines if you can find where to put them, can be extremely effective. So we always have this question of do you modify the compiler or work on the IL and the ILASM, ILDASM line level. We've avoided modifying the compiler so far, but one day we're not going to be able to avoid it anymore. It would let us overcome that particular behavior of the C# compiler that's not a bug, but it is a design decision that they've made and other people differ on. And right now the code is obviously interspersed through many classes in the JIT compiler, in the JIT interface, in the VM, VM classes itself, in the assembly loader, etc. So perhaps a cleaner solution using aspects somehow to insert that code would long-term be a better alternative. Okay. 30 minutes.